In this video, we will review the transformations of functions. So just as a refresher, we have what we call parent functions, and you should basically know the shape of the identity function y equals x, the basic parabola x squared, the square root of x, a cube function, a cube root function, the reciprocal function, and the absolute value of x. Now, interestingly, except for the reciprocal function, all of these go through the point 0, 0, and 1, 1. And that kind of helps us keep the shape of the function when we transform it. The reciprocal function does go through the point 1, 1, and then its kind of center is at 0, 0. So these are parent functions, and we've learned about the graphs of trigonometric functions, sine, cosine, tangent, cosecant, secant, and cotangent, exponential functions, and logarithmic functions as well. And all the transformation rules that we have work for all functions. So just as a refresher, we have a vertical shift, up or down. This is when you add to the function. So we're going to add some value, add to the function. A horizontal shift is when we add to the x before we apply the function. What you want to remember about your horizontal shifts is that if it's opposite of what you think. So for example, if you have f of x is x plus 2 squared, it's going to be to the left 2 units. Our reflections, if we put a minus sign in front of the function, then we're going to reflect on the x-axis. And if we put it in front of the x, we're going to reflect on the y-axis. And I like to remember these two by thinking about the function f of x equals x squared. We know that graph is a basic parabola. We also know that if we put a minus sign in front of the function, minus x squared, that it just reflects it on the x-axis. So here we're putting a negative sign in front of the function, and that will reflect it down. If, on the other hand, I put a negative sign in front of the x, that's going to be the negative of x quantity squared, which then is just x squared. And if we reflect on the y-axis, we can see that x squared reflected on the y-axis is just x squared again. Then we have a vertical stretch or shrink. That's if you put a constant in front of the function. So we can see that if our a value is bigger than 1, something like 2x squared, that our y values are going to be vertically stretched by a factor of 2. So rather than being at 1, 1, it's going to be at 1, 2, and it's going to be stretched up. Vertical shifts or vertical shrinks occur when your a value is between 0 and 1. For example, y equals 1/2 x squared. For our horizontal stretch and shrink, similar to our horizontal shifts, it's kind of opposite of what you think. So if you multiply your x value by a, and a, or in this case c, and c is greater than 1, then it's going to be a shrink. And if it's between 0 and 1, then it's going to be a stretch. So for example, if I have f of x equals 2x quantity squared, because I multiplied the x by something bigger than 1, this is actually going to be a horizontal shrink. So let's just take a look at some examples. Knowing what our parent functions are, when I look at y equals x squared plus 6, I know that x squared is a parabola, and this is telling me I should shift up 6 units, and it will have this shape. Here we have an absolute value, and we have two things going on. We've added to the 5, so this is going, or we've added to the x, we've added 5, and so this is going to be to the left 5 here. And normally it would just be a V shape, but we've put a minus sign in front of it, so the V shape is going to go down. And so this is where the information about the 1, 1 and the 0, 0 comes in, because I know it's just going to be 1 unit down and 1 unit over. And we have this here. All right, for this next one, we have a cube root. A cube root has this shape sideways, and this one, because I've subtracted 4 from the x, I'm going to shift it to the right 4. And other than that, it's going to be the up 1 over 1, down 1, back 1, and it'll look something like this. All right, here we have another absolute value. We know an absolute value has that V shape. That's how I remember that. This one is going to be to the right 2 and, right 4 and up 3. 1, 2, 3. So our vertex is going to be right here. We know we're going to go up 1 over 1, up 1 over 1, and we get this shape here. All right, just a couple more here. These are not the parent functions that we're used to seeing. These next 4 are a little bit different. We're going to start with sine of 3x plus pi. We did this earlier in the semester, but if you remember, we had to factor that 3 out so that we could actually see what our shift was. So we know a basic sine wave. This is telling us that we shifted to the left pi over 3. And this, if you recall, changes our period. So rather than be a period of being 2 pi, which is a standard period for sine, our period is going to be 2 pi divided by 3. So let's take a look at what that would look like. So here's our period. 2 pi over 3. Half of that would be pi over 3. This would be pi over 6, 2 pi over 6, and then 3 pi over 6, which is pi over 2. Our amplitude is 1. And we've shifted to the left pi over 3. So that's like 2 tick marks right here. minus pi over 3, and that's where we're going to start. So we're going to start here. We know sine goes up first, and our sine wave looks like this. Okay, for our next one here, we have an exponential function. And we've done a couple things to it. We've shifted it up 2, and we've also, if you look here, reflected it, and since it's in front of the function, it's going to be on the x-axis. So, a normal 3 to the x would go through the point 0, 1, and it might look something like this. That's just a normal 3 to the x. But we've done a couple things to it. Now, the question here becomes, do I shift it up first or then reflect it? And my answer is, if you are plugging a number in, let's say we plugged in the number 2, we would square the 3, and then we would make that 3 negative before we added the 2. So we're going to do the reflection first. The reflection is going to look like this. And then we're going to shift it up 2 units. And then this point here is going to be here. Our asymptote is going to be at 2. And it's going to look something like this. Just a sketch, okay? So we've got 1, 2, 3. And I should say each of these have the standard scale. Okay, 2 more here. Let's look at the logarithm first. You may or may not remember what a log function looks like, but in general, we know that if you just had log x, x has to be positive and not equal to 0. And we have this asymptote right here. And this is just a log base 10, but a log base 2 basically has the same shape. We're going to take this and we're going to shift it. Based on this, we're adding to the x. We're going to go left 1. So that means our asymptote is going to be to the left 1. So that's going to be our vertical asymptote. We were here at the point 1, 0, regardless of what your base is. So if you were at 1, 0 and you shifted it left 1, you're going to be right here. And our shape is going to be something like this. Now, if you wanted to have another ordered pair, you could do, for example, 2, even 1. You could plug in a 1. Log base 2 of 2 is 1 right there. Okay, our last example here. Cosecant of x plus 2. I'm hoping that you see this and you think, well, that's up 2 units. You may also think that this is related to the graph of sine x. So here in yellow, I am going to graph sine of x. We know the period is 2 pi. So breaking it up into quarters, we have pi over 2 and 3 pi over 2. And we know that an amplitude is just 1. So this is a standard sine wave. So to make this into a cosecant graph, we know that anywhere that sine is 0, which is at 0, pi, and 2 pi, that we're going to have an asymptote. And we would take these humps and valleys and reflect them to make these U shapes. So that this red, I'll make it red, this red is cosecant of x. But at this point, we want to shift it up 2. So rather than this being at pi over 2, 1, we're going to shift it up 2, and our U shape will go here. And then this one, instead of being at -1, is going to be at 1, and our U shape will go down like this. So sometimes I find it helpful to put all the different phases in there, but the black graph is really the graph in the end that we want. So if you need to erase those, you can. Okay, that concludes this video on transformations.